We present CoSi, a framework for visually comparing similarities in high-dimensional data ensembles. The design and evolution of materials is not only important in safety-critical industries such as aircraft and automotive. Materials in everyday products, for example the handle of this pen, have to meet certain properties like heat resistance and durability. To determine the properties of a material, specimens have to be analyzed through X-ray computed tomography. The resulting XCT scans reveal the internal structure of the specimen. Materials such as fiber-reinforced polymers can consist of fibers and pores. These features have certain distribution in the sample and have different characteristics such as length or diameter. A specimen can therefore be described as a high-dimensional tabular dataset. In their daily workflow, material scientists need to compare the internal structure of different specimens with each other, or analyze in situ tests. During these tests, a composite is exposed to a stress. The changing of its microstructures is recorded in discrete time steps, resulting in time-varying datasets. To enable an easy comparison of various specimens, the comparison of a specimen over time, and even the combination of both, we developed CoSi. CoSi offers an ensemble similarity explorer in which we can see the similarity among the ensemble members. Currently we see a fiber material that was subjected to a shear stress test. It was recorded after 10 minutes and then after 60 minutes of loading. For analysis, the material was divided into the same 4 regions for each recording. In this view, we can see the similarity of each region very well. In the similarity widget, a bar chart shows the similarity of the individual characteristics. In this example, the characteristics of the fibers are not very similar as all the bars are very small. The box plot gives us further details about the distribution of the characteristics. Here we can see that the fibers have a relatively small volume because the box of the box plots is very small and is positioned further below. In the correlation map, we can perceive the pairwise correlations of the characteristics. Here we can see the start and end values of the fibers are positively correlated. To examine the ensemble, we can first order the datasets to find out which contain the fewest features and which contain the most features. We can rearrange the data manually, and we can put the data back in the order in which it was originally loaded into the framework by the user. To get a more detailed view of the fiber distribution, we can increase the bin count by using the linear zooming function. To find the most similar datasets, a ranking can be performed. The ranking can be based on the whole dataset, it can be performed according to an individual bin, or it can be computed based on a group of bins. To examine specific bins in more detail, we can use the nonlinear zooming function. Here it is possible to zoom to the point representation. The bar chart, the box plot, and the correlation map react to the selection and show in green the calculations of the selected features.